Welcome back to Applied Mathematics. In this video, we're going to be looking at some applications of area. Let's get right into it. So here, we've been asked to perform a cost analysis for an upcoming project. The plans call for coating each of the 12 brackets depicted below with a protective sealant which costs $17.95 per ounce. If 1 ounce is enough to coat 15 square inches of metal, what will the cost be to protect these 12 brackets? Right. And if I scroll down a little bit, we can see that there is the bracket. And if I get my head out of the way, we have enough space to start writing some things down. Right. So the first thing I'm looking at is the fact that we're going to need area. Obviously, this is a problem from a section called area applications, so calculating the area will be important. But how do we know that? Well, I'm looking first at this phrase right here. 1 ounce is enough to coat 15 square inches. So I know that I need to find the area in square inches. I know that I'm going to use this material in the rate of 1 ounce per every 15 square inches. And then finally, I know that it is going to be $17.95 for 1 ounce. And I know that there are 12 of them. All right, so that gives me a 4-step process, the first step of which is finding the area. Of course, I've given us a not entirely straightforward shape whose area we need to find in the first place. So that means that this is going to take a little bit of doing, but it shouldn't be that bad. I'm interpreting this as a solid backing and then a bunch of holes cut into it. And it looks like there are 2 types of holes. So if I want to calculate the area of this whole thing, I'll describe it pictographically. I want to take the area of the rectangle minus 3 times the area of the tall slots minus 2 times the area of the circle. The rectangle is very straightforward. The circles are very straightforward. The tall slots are a little bit less so. But if you look at those closely, it looks to me like it is a half circle a rectangle, and then another half circle, all tied together. So I can split that up. I don't want to scroll quite that far down because I need the data still. And I can think about this as the area of the rectangle minus 3 times the area of the tall skinny rectangle that makes up part of that slot minus 6 times the area of that half a circle, and then minus 2 times the area of the full circle. If you think about it a little bit more carefully, 6 of the half a circle is 3 full circles. If you look even more closely, you'll notice that the two kinds of circles at this point are actually the same circle. I'm not going to take it that far, because at this point I have it broken down into relatively simple to work with pieces. The larger rectangle measures 7.50 by 2.25. The rectangular part of those three slots measures 1.25 by 0.30. Right? I have marked up here that there's these four things that are all that length of 0.30. And that 0.30 is going to be important here, because the area of a circle is pi times the radius squared. We're given that the diameter is 0.30. The radius is half of that, 0.15. And I've run out of space to put the last one in, but it's the same circle. Pi times 0.15 squared. All right. Piece by piece, 7.5 times 2.25 in three significant digits is 16.9, and that will be in square inches. Then I've got 1.25 times 0.30, and I've got three of them, so multiply that by 3. And then I only have two significant digits here, so my calculator tells me it's 1.125, but I'm going to call it 1.1. All right, then I've got pi times 0.15 squared, which comes out as 0.07, etc., etc. But I've got three of those, so it looks like that's going to come out at 0.21. And then the last circle, pi times 0.15 squared, and then two of those comes out at 0.14. So also paying attention to rounding here, I had a couple of values that had three significant digits, and I also had a couple of values that had two significant digits. So I ended up with three significant digits in that first measurement, and only two in the other ones. But now I'm going to be subtracting, and when I subtract, I use the precision rule. So I punch all of that into my calculator, it gives me 15.45, but then I look at all of my numbers and I realize that the worst precision is 1/10 of a square inch, so I have to round this and call it 15.5. All right, a lot of work. All we've done so far is found the area. But then the rest of this can be handled using the unit rates, right? There is 1 ounce per every 15 square inches, which is a little bit more than 1 ounce used for each of these devices. It's $17.95 per ounce, and there are 12 of them. So if I take my 15.5 square inches, and I multiply by 1 ounce over 15 square inches, and I multiply by $17.95 per ounce, and I multiply by 12. Well, the square inches cancel out, the ounces cancel out, I'm going to treat the 15 and the 1795 and the 12 as all being exact values, right? Those are kind of definitional. The 15.5, however, is approximate, and it has 3 significant digits. So I will round my result here. Yeah, my original inclination is I should round my result to 3 significant digits, but this is a money result. So part of me says maybe I should round it to the nearest penny. All right, so I think that calling it $223 is probably the right thing to do. But if you called it $222.58, I guess you wouldn't be wrong. The nice thing about calling it $223 is that it gives a little bit more clarity as, well, based on the approximations that I've used and based on rounding error that will come up through doing these calculations, that result might be off by $1. And when you're dealing with something that's 220 some dollars, well, that's it exactly. You're going to call it 220 some dollars per part. And that's probably good enough. You might also want to go back and consider, well, how do you have to purchase this? If you're only making one and you have to buy a 5-ounce container, well, that changes things drastically. I'm kind of working under the assumption that you're going to be mass producing these, or at least batch producing them. So the extra of the material in whatever size container you purchase is going to be negligible. But those are all things that might come up and would give you different results, which is a long way of why it's so important to show your work. Because if you show your work and you show that you're making an assumption about one thing or another, it can drastically change the result. And there's no reason that one or the other assumption is more correct when we don't have enough context to really say for certain. I know just one example that kind of feels a little bit fast, but I think that's enough, giving you the general flavor of we can do these sorts of things. So I'll wrap up with that. Thank you for joining me as always, and I'll see you in the next one.